And welcome back. Last week we talked a little bit about graphing motion in one dimension. Before that we talked about projectile motion, and before that we talked about accelerated and non-accelerated motion in one dimension. Projectile motion just being that in two dimensions simultaneously. Today we'll talk about Newton's laws of motion, which have everything to do with forces acting on objects and the effects those forces have. And so let's get started. We should talk about mass before we do anything. Mass, with the symbol m, is a scalar in that it doesn't have a direction, and this represents the amount of matter in a particle or object. The standard unit is the kilogram. Notice when you think about someone's mass, you never think of it as being 50 kilograms up or to the left, thus no direction, not a vector. The standard unit is the kilogram. And we should talk about the law of conservation of mass, which states that an object's mass cannot change unless some of its matter is added or removed. So the mass of an object, no matter where it is or how it's moving, always stays the same unless you change the object itself. Now, it's important to note that mass and weight are not the same. We use those two terms fairly interchangeably when we're just talking, but in physics, again, there's very specific definitions for both. Again, we talked about mass referring to the amount of material in an object. Weight, however, is the force an object places on its supports. So the weight of an object is how much force it applies to, say, the floor underneath it. That's also equal to the force of gravity acting on the object in most cases. If the object is stationary, that's true. We'll talk about some cases where that's not the case as well. Now, at the Earth's surface, a kilogram weighs about 9.8 newtons. But on Mars, because Mars is a smaller planet with less mass, that same kilogram mass only has a weight of 3.6 newtons. Why? Well, we'll talk about that. Shortly. But the gravitational attraction between two objects is dependent on the mass of the objects. Now, the kilogram mass hasn't changed, but moving from Earth to Mars, you're looking at the gravitational pull of Earth, which is fairly large, versus the pull of Mars, which is fairly small. On Jupiter, however, that same kilogram mass, because Jupiter is more massive, that same kilogram mass would have a weight of 24.5 newtons.